Hello, everyone. How are you? You good? You good? You fine? All right, so here we are again. This is, I think, the third episode of Complex Variables. Say hi to Remy. This is Remy. So, where we left off before, we left in question four. We finished question four, doing the proofs. Now, actually, I'm gonna need a second to set this up. Hold on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ok. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's imaginary. This is real. Alright, so you might wonder why I just made a coordinate plane. Well, I don't care. Uh, we're gonna do some visual representations of complex number operations, just like we did in the last chapter, but we're gonna do more in depth. Oh, for fuck's sake, come on. So I was saying we're gonna do a more visual representation of doing operations with complex numbers. So yeah. So number five, question number five says, perform the indicated operations both analytically and graphically. All right, we presented with a couple of operations. First, we get 3 plus 4i plus 5 plus 2i, right? Simple addition, analytically or symbolically or whatever. It's going to be 3 plus 5, which is 8, plus 4 plus 2 is 6, 8 plus 6i. Because you add this, and then you add this, just as if they were vectors. I would say, like I said, um, 2 episodes ago, right? So now, graphically, what this would look like if we have this coordinate plane, right? And we have the imaginary axis and the real axis, right? This is just like plotting vectors. It's gonna be 3 plus 5 is 8. 1, 2, 3, 4, 5, 6, 7, 8, right? Wait, actually, no, hold on. That's not how it goes. Hold on. 3. 1, 2, 3. Boom. For I. 1, 2, 3, 4. Boom. Now we draw. Hold on. I'll draw a straight line from here to there. We go boom. That's our first vector. And then our second vector is 5 plus 2i. 3, 4, 5. Boom. 2i. Boom. Right. Boom. Damn. Alright. So this is vector 1, vector 2, what are you going to call them? So to do addition with complex numbers is the same as just with vectors. Graphically, they're jointed. Uh, like, this is going to sound weird. Base to tip. So to add them, we can take either or, right? We can take vector 1, complex number 1, z1, whatever. Duplicate, duplicate, and put it on the tip, right? As you can see, this is 5, 6, 7, 8. Boom. What was this? This is 4. 4. And this is 1, 2. This is 6. Right? So the resulting vector is bam. How about that? It is what we said. It's 8 plus 6i. This is 8. And this is 6. So as you can see, it does go graphically, and it can go both ways. Yeah. We can duplicate this. If we duplicate this and we join it base to tip, we're gonna get the same answer. Right? So as you can see, with additional factors, you can some sort of a parallelogram, I think that's how you call it, gets created. And so yeah, that's how you visualize it. Hold on. Dang it. That's how you visualize it. God dang it, bro. Okay, I'm not gonna. Okay, there we go. Now, second one is it is 6 minus 2i, 6 minus 2i minus, subtraction, 2 minus 5i, 2 minus 5i, right? In the same way, we do with polynomials, you can do with, you can also do with vectors, and you can also do with complex numbers. Complex numbers, you can treat them as vectors. So you can rewrite this to be 6 minus 2i plus negative 2 plus 5i, and then you add like usual. So it's going to be 4 plus 3i. Right? Now graphically, a negative sign, you negate a vector, or in this case a complex number. What you get is like flipped. You know what I'm saying? I'm gonna try to visualize it. So our first vector is 6 minus 2i. We got 1, 2, 3, 4, 5, 6. Negative 2. Boom. There we go. I apologize for the slowliness. Just be gentle with me. This is my first time. Right? 6 minus 2i. Then we have 2 minus 5i. I'm going to do some. Hold on. 2. Is it 2 minus 5i? Yeah. Is it? Yeah. 2 minus 5i. 2. 1, 2, 3, 4, 5. Boom. Get this out. And we go. I think that's good enough. What? Actually, no, that's not good enough. It's supposed to go. There we go. All right. Now, this is Z1. This is Z2. What we're gonna do is again Z1 minus Z2, and which we can be rewritten as negative Z2. Right? So how do we negate a vector or a complex number graphically? Well, we just flip them. We flip them. I got confused. Hold on. We flip them, right? We take this, resize. We just go whip, right? 2 and 1, 2, 3, 4, 5. No, that's not it. Yeah, that's about it. Hold on. I want to get it like perfect, please. I think, yeah, yeah, I think that's, yeah. So the resulting flipped or negated vector or complex number is 2, oh, sorry, -2 and 5, right? And so if we add them like this, it's like we duplicate, we're doing base to tip. This is our resulting vector. Hold on. I'm gonna check it because I forgot what the result was. So I'm basically doing how it's supposed to be, like without doing the calculations. So our resulting vector is 1, 2, 3, 4. Okay, 4, 1, 2, 3, 4 plus 3i. There you go. That's how you do subtraction. That's how you negate a vector or complex number graphically. And this can also work just to show you guys. This can also definitely work both ways. If we duplicate, do base tip, it goes to the same place, right? With subtraction, hold on, bam, please. There we go. All right, now what's next? I think next is scalar multiplication. Is it? No, we have a multiple additions in a row. Uh, that's a little tedious, but just to get the point across. So we have -3 plus 5i plus 4 plus 2i plus 5 minus 3i plus -4 minus 6i. -4 minus 6i. Alright, I don't have my calculator with me, so bear with me. So over here, and -3 plus 4 is 1. 5 plus 2 is 7. 6, 7. Right? Over here, 5 minus 4 is 1. -3 plus -6 is -9. Right? We add, and we do 2 and -2. There we go. 2 minus 2i. This is what symbolically, analytically, the result of this whole summation is. Addition. English is not my first language, okay? So, this is gonna take a little while to. And I'm gonna have to name them because else I'm gonna get lost, very, very lost. C3, C4. There we go. All right. So Z1 is -3 plus 5i. We go 1, 2, 3, boom. 1, 2, 3, 4, 5. Boom. I want to do this accurately as possible, or else we're gonna get or I am gonna get a wrong answer. I want to make sure that it's as accurately as possible. Boom. This is Z1. All right. Almost lost the pen. Z2, 4 plus 2i. This is 1, 2, 3, 4. 1, 2. Bam. There we go. But here we go. Cool. I'm not gonna duplicate them, or else this time I'm not gonna duplicate them. Else it's gonna be a mess, a huge mess. 5 minus 3i. 1, 2, 3, 4, 5. 1, 2, 3. Boom. I could have gone through the extra trouble of numbering the axes, but I'm lazy. That's a price you pay for being lazy. There we go. Sometimes you don't find the most optimal solution right away if you're lazy. Z3. Alright, one more. -4, -6. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Move. There we go. And hold on. I want to make sure it's perfect. I want it to be as perfect as possible. I need it to be perfect. Anyway. All right, there we go. Z4. All right. Okay. So, Remmy, no. All right. Hold on. We got Remmy. We got Remmy back. I'm sorry, Remmy. All right. So let's get to adding. We do the same. It's the same process. It's like Z2. Boom. Yes. Not gonna copy it. Z2. Tip to base. There we go. Z2. Z3. Z3. Boom. Tip to base. Yep. And then Z4. Boom. Tip to base. I think that's supposed to be, yep. Okay, so what we're left with is this result vector, which is, oh, that's very nice. Is what? It's, huh? Is that supposed to be, hold on. This is weird. What did I do wrong? Wait. So it's 1, 2, 1, 2, 2. Oh, 2, -2. I completely forgot the result. I completely forgot the answer. Yeah, that's the answer. That's the answer. Yeah, there you go. That's how you add and subtract graphically with complex numbers. This also applies to vectors. And what else did I apply? Nah, only to vectors. Only applies to vectors. Sadly. All right. So, question 6. Okay, this might be a proof. Is this a proof? No. Okay. I'll see if I can do it. I don't remember. It's been so long since I've gone back to. I think I'm always gonna be saying that. Because it's been like 2 weeks since I've last seen this book. Well, question 6 says, if z1 and z2 are two given complex numbers, vectors, right? Construct graphically. All right. A. We gotta construct it graphically. 3z1 minus 2z2. 3z1 minus 2. Oh god damn. C2. B is z2 over 2 plus, what's that? What's that number? 5z1 over 3. 5z1 over 3. Right? Is there a third one? No, there's not a third one. It's just these two. Alright, so let's keep it simple. Let's keep it like single unit vector 1 1 is just an example, just to illustrate it, you know. You know what? No, let's make it interesting. I'm gonna pick a random point in this hold on, in this coordinate plane, and I'm gonna get my assistant. Elige un número aleatorio. Dame un número aleatorio.
¿Cuál es el range?
Anything. Del 0 al 10.
5.
¿Y otro?
7.
Okay, we got 5, 7. 1, 2, 3, 4, 5. There we go. Boom. We go 1, 2, 3, 4, 5, 6, 7. Boom. Wait, that's 7, right? 2, 3, 4, 5, 6, 7. All right. And that's our. Hold on. Boom. All right. That's our first aleatory. Not aleatory. I'm saying it in Spanish. Our first random complex number. This is going to be our z1. Right? Dime otro número. Dime otro par de números.
6. 7.
We got 6, 7, 6. Okay. We got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. All right. So that's our second. Fuck. That's our second fuck of the day. I don't have no more fucks to give. Sadly. This is a Z1, this is Z2, right? I do not remember the exact measurements of Z1 and Z2 anymore. I don't want to hear Z2 again. So this is completely random. It's gonna work. It is sure to work. So 3Z1. So this is introducing scalar multiplication of complex numbers or vectors. Same thing. Scalar multiplication. So the way it looks graphically is you basically just triple the length, right? So you take z1. Hold on. That should be z1. Duplicate. There we go. Take the top as best as you can, and then duplicate again. Duplicate. Boom. Duplicate. There we go. Oh, I just remember the measurements. Okay. So let's have 6, 7. Anyways, So I have, so if we multiply this by 3, 3z1 equals 15, 21, right? Z2 equals, what was 2? Okay, 12, 12, comma, 14. Hold on. All right, so we just got done doing 3z1. Um, I'm not gonna count that. You feel free to pause and then count the dots. I am not gonna do that. Have fun. So 2z2, more manageable. So we do the same with z2. We do 1, 1, boom, and then we duplicate, boom. There we go. That should be it. All right. So the way we add them is still the same. I'm gonna take the smaller one. Ah, come on. Ah, better not. I'm gonna take this smaller one. Man, fucking let me get just a Z1. Please. Please. Actually, Z2. 2Z2. And I'm gonna duplicate just for the fun of it. Duplicate. Here we go. And if we got tip to toe, boom, that should be it. That is it. Right? I'm trying my best, okay? Don't laugh. Don't if you laugh, you're banned from the channel. That's what I said. I said what I said. I don't care. I said I didn't have any more fucks to give. Alright, so our answer should be what's 15 plus 12? It's 27. Then 21, that's 14, that's 35. 27 and 35. That makes sense because it's all the way out there. Now for my second trick, I'm gonna get some smaller numbers to work with. Actually, no. I'm gonna get the same numbers. Uh, hmm. No, I'm not sure. Should I? Mm, actually, let's change it. I'm gonna change the 7 because it's easier to illustrate it, to have an accurate representation of the vectors if they're not decimals, right? So 6 times 5 is 30 divided by 3 is 10. Yeah, good. So what I'm gonna do is the following. Why didn't I delete? There you go. Delete. What I'm gonna do is the following. 6, 6, right. So we go 1, 2, 3, 4, 5, 6. Oh no. 2, 3, 4, 5. Boom. 1, 2, 3, 4, 5, 6. Boom. All right. So now, hold on. Fuck. Okay. Please work. Okay. Now, boom. This is Z1, right? I was thinking that I had a brain fog, some crazy brain fog. 6, 6, 6, right? Oh, right. Fought. There we go. Stay with me. Stay with me. I know this is kind of low, kind of slow. Stay with me. I need to draw this all by myself. So the operations we have is divide by 2 and then multiply by 5 and then divide by 3. So Z1 over 2. Oh, I have a 4, 6 it is. I apologize for the inconvenience. 4, 6, 4, 6. There we go. Boom. I did not notice that 5 divided by 2 is a decimal. I don't want to work with decimals right now because we're doing um, decimals and fractions because we're doing visualization and it's much nicer to have whole numbers. So Z2, I mean Z1 divided by 2, I changed it to 4. Z1 divided by 2 is 2, comma 3 because 4 divided by 2 is 2, 6 divided by 2 is 3. Then Z, wait, what? Oh, it's Z2. Oh, never mind. Might be. It's actually Z2 over 2. I don't know what's happening today. It's something's been off lately. Z2 over 2. What was it? 2? 3, 3. Z1 times 5 over 3. Yes. 4 times 5. I'm sorry. 4 times 5 is 20. Divided by 3. You know what? Screw it. I'm gonna keep the decimals. This is 20 over 3. 20 over 3. And then 6 times 5 is 36. Divided by 3 is 23. Right? No, 13. Is it? Hold on. What? I'm having such a brain fog today. C1. Alright. 5 times 6 is 30. Divided by 3 is 10. Ah. So. 5 divided by 3. 10. What's 20 divided by 3? Let's do some quick. My considerate assistant just allowed me to have a calculator. ¿Qué digo? No sé qué digo.
Está bien, mi amor.
¿Ah?
Está bien.
Ah.
Necesito asistente.
Ah. Oh, no. You know what 20 divided by 3 is? 6.67. I tried avoiding 6, 7 this whole time. It's bro. Oh my god.
Yeah.
Bro. So, So we got 3, 3 comma 3. 1, 2, 3, 1, 2, 3. This is Z2 right here, right? And then 6.67 comma 10. This is 1, 2, 3, 4, 5, 6. This is approximately a half, 6, 7, right? So if we go over here and we want to go 10, we have it right here. That's our dot. Oh, forgot I had it on. That's our dot. And I'm gonna put it as best as I can. Oh, actually, just gonna. There we go. Z. No. Yeah. No. Yeah. That's about it. And there we go. So that's our stuff. And if we go up 3, 1, 2, 3, 1, 2, 3. That's about there. It should be. This is such a mess. And we add them. Obviously, we have to add them. I'm going to use fractions because it's easier for me to work with fractions at this point. So 3 plus 20 over 3 is the same as 6, actually, 9 over 3 plus 20, 29 over 3, get it, right? And 3 plus 10 is 13, so that's our answer. What's 29 over 3? 9.67. Oh my goodness. As you can see, it pretty much is 9 because this is 9.67 and this is 10, 11, 12, 13. Yep, we got it. We I couldn't find a way to work around fractions, honestly. It's just I don't have that much brain power left today. All right. Next question. Next is the question. Uh, oh no. Oh no. Um, wait, what? We got some proofs to do. But I'm not really gonna do the proofs because my little monkey brain is not capable enough to actually prove this. Um, yeah, yeah. So we were working with absolute values in this question. This is a three-part question. It's just prove three theorems, right? First theorem is the absolute value of z1 plus z2 is uh, less than or equal to absolute value of z1, right? Z1 plus the absolute value of Z2. There we go. Boom. So we got to prove it. I'm not going to prove it. I don't have you know, I'm just going to show it right now. I'm just going to show it, and that's it. So, why is this true? So, we must look at it graphically, right? It's better to understand it graphically. So, take a random point. Take here, right? Boom. That was awful. I'm gonna try to explain it to the best of my capabilities. There we go. Policy 1. take another random point down here, right? Again, awful. I tried. Uh, get another this random point over here. Get another random point from a vector and call it z2, right? The absolute value of z1 and z2. Actually, z1 plus z2. Let's graph it. Duplicate. Boom. Right? That doesn't really get. There we go. So z1 plus z2 is this. Right? That's what it is. Right? I don't know what it is. Let's call it p. Just because I like p. So, what was the theorem again? The absolute value of z1 plus z2 is less than or equal to. Right. So as you can see, this also has to do with the angle between z1 and z2, right? Why does it matter? Because this can only be true if um, the angle between z1 and z2 is 0. So basically, they're um, scalars of each other. Because if you see right here, this angle theta is the same as this angle right here, theta. So as the angle increases, excuse me, as the angle increases, this is also going to go down, and the length of phi is also going to go down. Right? And as the angle decreases and approaches more to a straight line, p is going to be equal to z1 plus z2. That's how I can explain it, right? I know how to get to an equation, but it's like the logic as to why that is true is really it doesn't stick with me. It's like, how do you know that it has to be less than or equal to and not just equal to? You know, it's like it's easy to see it graphically, but it's like analytically, I couldn't find a way to prove it. Um, it's gonna be my first loss of the book. Um, and it is basically the same with the more vectors you add. It's like, let's add another vector, right? Why not? This one. There's 1, 2, 3, 4, 5, 6. 5 and 6. There you go. 1, 2, 3, 4, 5, 1. Boom. Right? Let's call this phi, just because. Right? As phi increases, this is gonna as phi increases, this is gonna go down, and this is gonna go down, and the value of p2. Yeah, p2. I'm explaining it quickly. That's why I'm not. The absolute value of p2 is gonna go down. It's basically how it works, right? Basically the angle between the three vectors, the lower it is, the closer the absolute values are gonna be the same. The higher it is, the more different. I think that's how you say it. But anyway, this is my first loss. It's hard to say. It's hard to say. I've gotten to the first loss of the book. The book has gotten the best of me, right? The next question is this. Um, I think I think we have time for another one. Let the position vector swing represent respectively. The vector A, B is a complex number. Find the distance between points A and B. All right, we can do it. We can do this. All right. So, uh, let's take a random number. I'm gonna get my assistant to tell me some random numbers. Dime otros números aleatorios que no sean 6, 7.
Hasta el 10.
Sí.
2 y 8.
So we got 2 and 8. 2. 1, 2, 3, 4, 5, 6, 7, 8. Boom. Right. We got 2 and 8. Boom. Right, right. And 8. Dime otros dos números.
¿Mm?
Dime otros dos números.
5 y 9.
5 and 9. 1, 2, 3, 4, 5. 1. 1, 2, 3, 4, 5, 6, 7, 8, 9. I was like, I don't want to have a say in like deciding which points to use because I want to show that this applies to any combination of vectors, complex numbers, coordinates, anything, right? This is actually, let's plot the points. This point A, this point B. That's what the question says. Like, let point A, x1, y1, B, x2, y2, right? And it's asking us to find the distance between A and B, right? Right. So, so to like go back to kind of first principles, let's look at how you find the distance between 2 points on the real scale, right? So we have this real. I like to make good symbols. I like to make good symbols. I'm gonna. Oh, that was good. Anyway, we got 0. Let's say 5, -3. We can also do 7, because why not, right? So the way we find the distance between these 2 points, right, is by subtraction, basically. So we take 5, subtract 7. That's the distance between 5 and 7. It's going to be represented, which is 2, represented over here in absolute terms, right? And it's the same when we go to negative numbers. So if we want to find the distance between 5 and -3, we do 5 minus -3 or -3 minus 5 and do the absolute value, right? Which is going to be 8. So if we take this and we basically move it out to 0, the distance is going to be 8. So it's basically the same. It's basically the same concept. We just subtracting vectors. So to find the distance between A and B, let's call it P, because why not? We got to subtract A and B, and then take the absolute value, right? So I'm gonna try to do it algebraically. So we have fuck. So we have x1, y1 minus x2, y2, right? Like I said before, you can rewrite this as this. so you can see it better. It's okay to rewrite things and like put them into other perspectives so that you can solve a problem, right? Like your brain doesn't work the same as my brain. My brain doesn't work the same as anybody else's brain. We all need different things. We all need to see different perspectives to solve some problems. As long as we solve the problems, that's what matters, right? Personally, I like to distribute the negative sign. Basically, don't judge me. Stop laughing. Uh, so yeah, so we add them. It's x1 minus x2. Again, y1 minus y2. And now we take the absolute value, which is like taking the magnitude of a vector. So it's going to be x1 minus x2 squared plus y1 minus y2 squared, square root. Uh, since we got some time, like uh, I can try to evaluate this. So it's gonna be x1 squared minus 2 x1 x2 plus x2 squared. Oh, Remy, Remy, no. There we go. All right. So there's gonna be plus. We have y1 squared. I said there we go. Y1 squared minus 2 y1 y2 plus y2 squared. Boom. Square. We can maybe not. Yeah, maybe not. Let's leave it like that. So that's basically how you do it algebraically. Graphically, you're gonna take, let's say B. Let's take B, and we're gonna flip it. We're gonna take it. We're gonna duplicate it. Actually, I'm gonna put it right where it was. Now we're gonna flip it. Resize. Right. So it's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. 5, 9. This is gonna become negative 5, negative 9. So we go over here. I said we go over here. Okay. 1, 2, 3, 4, 5. Right? Fucking stay. It's not staying. Just gonna keep it like that. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? Nobody saw it. Anyway, now we take this flipped thing. I know it's not the most perfect thing, and we put it base to tip, right? What we get is should be something like this. Well, right. So what were the two vectors? 5, 9. That was B. A was 1, 1, 2, 2, 8 was 2, 8. So 2, 8 minus 5, 9. So this is going to be negative 3, negative 1. Right? 1, 2, 3, 1. Right? We got it. We got the difference. That's what we got. We got this. So now, to get the distance between them, we're gonna calculate the absolute value of those two numbers of the subtraction. This is gonna become 3 squared plus 1 squared. So it's gonna be square root 10. So the difference So the distance between points A and B is square root 10. That's how you do it. That's how you do it. That's how you do it algebraically. That's how you do it uh, graphically, right? So um, we've worked through quite a bit number of problems. I would work through 5, 6, 7, and then number 8. Right, that's what I'm saying. So 4 problems. 4 problems in an hour. That's actually pretty good. Pretty good math work. And so what we did today was uh, we did some basic operations with complex numbers, and we did them graphically, right? Like so, addition, subtraction, scalar multiplication, and I tried to prove some theorems. I was just able to solve them. I couldn't do anything more. Um, and then uh, we learned about the how to calculate the distance between two complex numbers in graphically and um, what was it? Graphically and algebraically. So yeah, that's the whole video. If you liked it, like the video. If you want to see more videos like this, subscribe, hit the like button. Yeah. All right. See you in the next one. Bye.